From record heat to raging storms, something strange is happening with the weather.
Global warming is real.
Or is it?
There is no basis to say that more CO2 in the air is going to lead to catastrophic global warming.
But what do we really know about the greenhouse effect?
You're dealing with something where there's legitimate uncertainty in science.
Is there a real solution to our dependency on fossil fuels?
If humankind is going to have a future on this planet, it is absolutely inevitable that we're going to have to find another energy source.
And does America and the world have the political will to tackle what could become the most troubling issue of the 21st century?
The notion of reducing carbon dioxide emission levels by the year 2010 is a complete fantasy. We are not going to do it as a society.
Tonight, PBS's premier science and investigative series join forces to investigate the truth about global warming.
Funding for NOVA and Frontline is provided by contributions to your PBS stations from viewers like you. Thank you.
For most of history, humans believed that the weather was governed by forces outside their control. But today, we're no longer so sure. Something weird, it's claimed, is going on with the weather. From storms and hurricanes to droughts.
Withering heat waves in Texas and in Florida. Cities that are setting 1,000-year records for high temperatures. How much more proof do we need that global warming is real?
And the future, some argue, could be apocalyptic, as ice caps melt and sea levels rise as much as 20 feet.
Over the last few years, you begin to get increased probability of extreme events. You're beginning to get a sense that these things are happening more than they used to. And people are beginning to connect that with global warming.
Vice President Gore is so convinced humans are warming the planet, he advocated an international treaty committing America to drastically reduce emissions from oil, gas, and coal. Burning these fossil fuels, he argues, puts greenhouse gases into the atmosphere, which trap heat and warm the globe. His opponents object that the risks are exaggerated, and any attempt to limit or get rid of oil, gas, and coal, which provide 90% of our energy, will cause an economic apocalypse, from job losses to recession.
This is the United States government identifying with a policy that would be devastating. What the long-term goal of the Vice President of the United States is to ultimately eliminate all fossil fuel use in the United States. That is their goal.
At the heart of this contentious issue is a battle for the truth. When we strip away the rhetoric and politics, what does science really know about global warming? The question has pushed the once obscure science of climatology into the spotlight.
Okay.
But the climate system has turned out to be very complex.
Spectacular. But now we're getting near the end of the run where the CO2 level is much more than double present day.
And scientists' pronouncements about the future of the planet vary widely as they struggle to determine whether the changes in the climate are natural or caused by human beings.
A 5-degree warming will just change the whole climate system radically. Precipitation patterns will be entirely different. The amounts of precipitation will be entirely different.
The climate changes, whether or not human beings have something to do with it. You know, there's this little anomaly called the Ice Age. The Earth's climate naturally goes from its current state to having 5,000 feet of ice over Chicago. The climate is unstable.
Tonight, Nova and Frontline set out to uncover the truth about global warming. A lot is at stake.
Any new climate treaty must not result in serious economic harm to the United States. What could be more basic than that?
From the wealth of nations to the future of the planet. Are humans warming the globe? Or are we an insignificant influence compared with the natural forces which have determined the climate for millions of years?
If you sat down and said, I'm going to design a public issue that is the absolute worst nightmare of every scientist, of every communicator in the world, you couldn't do better than the greenhouse effect. You're dealing with something that's very complicated. You're dealing with something where there's legitimate uncertainty in the science. It's not that people are trying to pull the wool over anybody's eyes. There's legitimate uncertainty. You're dealing with something that has enormous consequences for people. And you're dealing with something whose effects will happen 30 years down the road, you know, when they happen. And then you say, you give people this and say, okay, do something about it.
It is, in fact, a heat wave of global and historic proportions. Much more than just
the issue is typically framed in the media as a simple question. Is it getting warmer?
Figures in from Canada today show October '98 was the warmest October on Earth on record.
Caused power dips that delayed subway service.
Unfortunately, when people talk about global warming, it's always in terms of, oh gosh, it was hot last summer. And that doesn't work because weather and climate are two very different things. Climate is sort of long-term things. Weather is short-term, daily, hourly, monthly, whatever. And what we're talking about when we talk about the greenhouse effect is we're talking about climate.
James Trefil is a physicist and science writer who has followed the global warming issue closely.
In order to say it is actually getting warmer now, you have to know what it's been in the past. And you have to know that what you're seeing is not just a fluctuation. I mean, I remember when I was a kid in the 50s hearing stuff about the coming ice age because we were in a kind of a little cold snap then. And I remember pictures in the covers of magazines showing glaciers moving down across American cities. So if you take any short-term timeline, any short-term database for temperature and extrapolate it, you can get to crazy results. In order to make an incontrovertible case for global warming, you'd have to have a long-term temperature record, centuries, that was over a large part of the globe. And so you have to look over a long term and say, what's the average been for several hundred years, and is this a significant departure from that? And that's what's very difficult to do.
Bad weather in one place at one time does not prove the climate is changing. To prove humans are warming the globe requires detailed knowledge of the entire Earth's weather over long stretches of history. And this has turned out to be an enormously complex scientific challenge. The Earth is a big place. 3/4 of it is covered by water. There are giant ice caps, and deserts and mountains. But climate scientists somehow need to take the Earth's global temperature. Today, the Earth's weather is measured daily all over the globe by an international network of stations on land and sea, which report temperature, pressure, rainfall, humidity, and a host of other variables. Such global measurements are the prime database for climatology. Millions and millions of figures have been collated, corrected, adjusted, and synthesized. The problem is these measurements have only been taken systematically for a century. When averaged, a pattern emerges. During the past 100 years, the global surface temperature has risen by 1 degree Fahrenheit, or about ½ degree Celsius. This is a temperature record of the entire Earth's surface, not just the weather in one place. But is a 1 degree rise over a century a little or a lot?
What's really remarkable about the warming over the last century is both its magnitude, in terms of ½ degree Celsius, and its fact that it's been almost worldwide. Almost every site you look at has warmed dramatically since the middle of the last century.
But not everyone's convinced this is evidence that humans are warming the globe. Fred Singer, an atmospheric physicist, is one of a small band of scientists who have become known as greenhouse skeptics. He argues that the 100-year record is not what it appears to be.
The data are ambiguous. For example, the data show that the climate warmed between 1900 and 1940, long before humanity used much energy. But then the climate cooled between 1940 and 1975.
Only in the last few decades do rising global temperatures seem to coincide with the greenhouse gases we put into the atmosphere. Skeptics like Singer have also argued that long before the Industrial Revolution, the climate warmed naturally. For example, records show that in the Middle Ages, parts of the world like Greenland were warmer than today. The Vikings built settlements there and farmed the land.
The Vikings were able to grow crops, and life was good in Europe. Cathedrals were being built. There was plenty of food. Climate change is a natural phenomenon. Climate keeps changing all the time. It's either warming or cooling.
But records of one place, like Greenland, during one time, the Middle Ages, may not prove anything. Only by knowing the average global temperature 1,000 years ago can scientists know whether the Earth back then was warmer or colder than today.
What we're looking for is a period in the past, or periods that were as warm or warmer than today. Because of course if they were that warm, they were probably that warm due to natural processes. And that might give us some clues about what natural processes, as distinct from human ones, could be causing the warming today.
Long before thermometers were invented, human beings recorded the weather, sometimes in great detail. And these records are now being scrutinized by climate historians.
Weather was an extremely important variable in daily life, and most people worked outdoors, and they were outdoors for most of the day. They were much more vulnerable and they knew it, and for this reason there was an extreme interest in any kind of predictions.
Throughout history, there have been people who documented events regularly and meticulously. Physicians, artisans, and the monks here at Einsiedeln in Switzerland. They recorded the time the cherry blossom appeared, the freezing and thawing of lakes, the state of the wine harvest.
For instance, a very early cherry blossom is always related to a very warm month of March. If the Lake of Zurich is completely frozen, we know that it's equivalent to 2 extremely cold months, always, because we know it from the period when we have both the observations and the measurements.
From these diverse records, climate historians can glean a lot about the past climate. By combining data from many sites, this clever forensic work can yield a detailed picture of areas like Central Europe going back more than 1,000 years. Has Pfister found any period in the past as warm as the 1980s and 90s?
We had other periods which was also very warm, but it was equivalent to the 20th century prior to 1988, I would say. This was a period of warm climate, but I would say it was a period of warm natural climate. To the period between 1988 and 1997, there is absolutely no equivalent as far as I can look back.
But this technique too is limited. Only a few areas like Europe have long-term records which survive. To get a handle on the global climate, scientists have been forced to go beyond human accounts of the weather. 500 miles from the North Pole, a frozen lake will be home to a team of scientists for the next few weeks. It's part of an international effort to try and reconstruct the climates of the past.
We're here in the Canadian High Arctic on Ellesmere Island, about 500 miles from the North Pole. And it might seem strange that we would come to this kind of environment to study the problem of global warming. But what we need to do is to try to reconstruct the longer-term history of climate. And we do that by using so-called natural archives of climate, things that in some way retain in their structure a measure of how the climate has varied in the past.
Bradley and his team will spend the brief Arctic summer drilling through the ice and sampling the pristine sediments at the bottom of Lake Tuborg.
Because the lake is frozen over for most of the winter, what we have is a very brief period during the summer when the snow melts and the sediments are carried into the lake, and that settles out into the lake, and it forms these layers, just like the layers you see in a tree ring or in an ice core. Year by year, we get a nice sedimentary record.
These year-by-year variations in thickness will be used to estimate past temperatures at Lake Tuborg. A thicker layer means there was a warm spring, which melted more snow and produced more mud.
Wow, that's great. Look at this here. Wow, look at that.
This expedition yields temperature information going back hundreds of years, but in just one location. To estimate the past average global temperature, such measurements must be made all over the Earth's surface. 3,500 miles to the south, a team from Scripps Institution of Oceanography are examining the trees in Mammoth Park, California. Franco Biondi and his colleagues have done this many times.
The way the trees grow, they will cover themselves entirely every year with a new layer of wood. And if you take a horizontal section, you're going to see the width of each one of these layers.
Because trees grow all over the world, they are one of the most powerful natural recorders. Their annual rings not only give scientists a built-in date, they also contain a record of past temperature and precipitation.
Each one of these layers is an annual layer seen in cross-section. The annual layer is formed by these two portions together, the early wood and the late wood. And the width of the layer is our first indication of a climate pattern. So the narrow band that you see here indicates a year when the winter and spring were drier than normal, and then the larger layers that you see here indicate a period when winter and spring precipitation were more abundant than normal.
Trees are very common on land, but for the 3/4 of the planet covered by ocean, scientists need other recorders. Like trees, corals can live for hundreds of years and grow at different rates depending on the temperature at the sea surface. The Earth's temperature is also preserved in the chemistry of ice layers extracted from glaciers all around the world. Each natural recorder produces estimates of temperature and rainfall for a given place and time. Combining them all, scientists have been able to extend back the temperature record for the Northern Hemisphere about 1,000 years. According to this graph, published in 1999, the 20th century's 1-degree warming stands out dramatically. But what about Greenland, and its controversial medieval warm period. According to the combined data, there was no medieval warm period. Specific regions like Greenland may have been warm, but the average global temperature back then was cooler than today. Even though the data is preliminary, Bradley is convinced the climate of the 20th century is unprecedented.
We think this warm period 1,000 years ago was just a regional anomaly. We find almost no period in that whole 1,000 years which has temperatures as high as we've seen in the last part of the 20th century. And in particular, the 1990s were exceptionally warm. It was an incredibly unusual decade. And we have no evidence that there was a decade quite like the 1990s, all the way back 1,000 years.
If this finding holds up, does it prove humans are causing global warming? Some greenhouse skeptics like MIT's Richard Lindzen urge caution.
Well, it leaves out a couple of things. First of all, one has to distinguish the statement warming, meaning temperature has gone up, from warming, meaning man has caused temperature, or something has caused temperature to increase.
How can we be sure that recent warming is man-made rather than natural? And what evidence is there to link this temperature increase to human activity? Perhaps no man has done more to help answer this question than Charles David Keeling. 40 years ago, nobody knew for sure whether industrial greenhouse gases like carbon dioxide were increasing in the atmosphere or whether they were being absorbed by the oceans. In 1957, Keeling set out to discover which was right. Taking advantage of the special funding available in the International Geophysical Year, he set out with the latest analyzers to begin what would become his life's work.
This program afforded me an opportunity, even though I was just out of school practically and a very young man, to commandeer enough resources to see that these analyzers were put in several places, and rather quickly at that. One analyzer was put in Little America, Antarctica, and shortly after, another one was placed on a mountain in Hawaii called Mauna Loa.
The ideal place to measure carbon dioxide is away from cities which produce it, and distant from vegetation which absorbs it. On the Hawaiian mountain of Mauna Loa, Keeling found the ideal spot. Located at 11,000 feet in the midst of a barren lava field, he began to sample the Earth's air.
At Mauna Loa Observatory, we started the measurements in March 1957, and I expected the concentration would be perhaps almost dead constant, knowing nothing else as a hypothesis. But that wasn't what happened. The concentration rose for the several months, and then it dropped. And it dropped all during the period from May until September. And then it started to rise again. As soon as we saw that much information, less than a year's worth of data, it was pretty obvious that we were looking at the breathing of the plants in the northern hemisphere, because they absorb carbon dioxide during their growing period in temperate and high latitudes. And then it's released again in a cyclic process in the wintertime.
Keeling's sensitive measurements had picked up the Earth's respiration. Every spring, plants bloomed, sucking carbon dioxide out of the air. Every fall, CO2 was released back into the air as the plants decayed. But Keeling noticed that year by year, the total concentration of CO2 increased. Superimposed on the annual cycle was a rising curve. Each year, more CO2 was inhaled and exhaled by the biosphere. Over 40 years, the concentrations rose from 315 parts per million to almost 370 parts per million. The Keeling curve appeared to prove what many had suspected. that humans were changing the composition of the atmosphere. But why should adding an invisible, non-toxic gas be cause for concern? Compared to the major atmospheric gases, oxygen and nitrogen, the amount of CO2 is minuscule. But through an accident of physics, the greenhouse effect, its consequences are significant. Perhaps the most dramatic example of the greenhouse effect is the Earth itself. But for this effect, the Earth would be frigidly cold. Of the energy coming from the sun, about half of the light gets scattered and absorbed before it reaches the surface. The rest is radiated back as heat or infrared radiation. In the absence of a greenhouse effect, this heat energy would escape back into space, leaving the Earth with an average temperature of 0 degrees Fahrenheit. All water would freeze. The reason this doesn't happen is that greenhouse substances, gases like carbon dioxide and methane, and water vapor and clouds all act to trap escaping infrared radiation. The net effect is to cause the Earth's surface to warm up to an average of 59 degrees.
It's as real as gravity, and it keeps the planet habitable. We'd have an average surface temperature on the Earth below the freezing point of water were it not for the greenhouse effect.
But since the Industrial Revolution, there has been a new and growing source of CO2, fossil fuels like coal, oil, and natural gas. When fossil fuels are burned, their carbon atoms combine with oxygen in the air to make CO2. Every time we turn on a light or drive our cars, we are adding CO2 to the atmosphere.
It's hard for people to understand how much carbon dioxide is being put in the atmosphere in absolute terms, but in relative terms we can say as follows. At the end of World War II, about 1 billion metric tons of carbon in the form of CO2 was being emitted to the atmosphere. When I started my measurements, it had risen to 2.5. At the present time, it's almost 7.
According to the theory of the greenhouse effect, adding more greenhouse gases like CO2 to the atmosphere should cause the average global temperature to rise for as long as we continue burning fossil fuels. The climates of Mars and Venus were also shaped by the greenhouse effect.
Venus has an extremely high concentration of CO2 in its atmosphere, and it's blazing, boiling hot at the surface of Venus. And the Martian atmosphere, for instance, is very, very thin, and also within that thin atmosphere there's only a very, very small amount of CO2, and water vapor is also very, very low. And the surface temperature of Mars is frigid, very, very cold.
In the contentious debate about man-made global warming, all sides agree on the physics of the greenhouse effect. It can even be demonstrated in the lab using a FLIR thermocam, a special infrared camera.
So we're going to demonstrate to you how the CO2 absorbs infrared radiation, which causes the Earth greenhouse effect. Infrared radiation is another word for heat radiation, which is coming off my face, and which is picked up by a camera that I'm looking at. The camera is sensitive to heat radiation. Between me and the camera is a volume that we will fill with CO2 gas. And as we turn on the gas, my image will slowly fade.
This physical property of CO2, known to physicists for a century, is the bedrock of the concern about global warming. Because the ordinary air in the tube, composed mainly of nitrogen and oxygen, does not block infrared radiation, the camera sees the heat coming off the scientist's face clearly.
And as we turn on the gas, my image will slowly fade.
But when the tube is filled with CO2, or any greenhouse gas, Their molecules absorb the heat radiating off his face, blocking its path. As less and less heat reaches the camera, the image fades. If the scientist were surrounded on all sides by CO2, then the effect would be for him to get warmer, like the Earth in space. Today, the atmosphere is sampled at many sites on land and sea. Flasks are filled and sent to central laboratories, like the National Oceanic and Atmospheric Administration Lab in Boulder, Colorado, to be analyzed for CO2 and other greenhouse gases. Even though most of the CO2 is put into the atmosphere in the industrial northern hemisphere, analysis reveals it pretty soon shows up everywhere.
If you burn, say, a gallon of gasoline that's turned into CO2 molecules, it will spread throughout the entire atmosphere. So what you burn today in your car will show up in Antarctica by next year.
The other important fact scientists have discovered about CO2 is its permanence. Unlike water vapor, which stays around only for days, CO2 remains in the atmosphere for on average 100 years before being absorbed by the oceans. Our CO2 emissions are therefore changing the atmosphere not just for us, but for future generations. The measurements at Mauna Loa had produced clear evidence that humans were changing the composition of the atmosphere. But the data went back only 40 years, while we've been burning fossil fuels for more than 150 years, all during the Industrial Revolution. Just as scientists had used natural recorders to get at past temperatures, they now wondered if the giant ice sheets in Greenland and Antarctica might have captured past CO2 levels during and before the Industrial Revolution. And what they found was remarkable. Trapped in the ice cores are bubbles of air, time capsules preserving the atmosphere of the past. With care, these bubbles of fossilized air can be analyzed for carbon dioxide and other gases. Sensitive analysis of the air bubbles reveals that before 1957, the atmosphere had less CO2. Indeed, CO2's rapid rise starts at the beginning of the Industrial Revolution. Subsequent research has extended the curve far back in time. It's now established that current levels of CO2 are higher than at any time for the past 450,000 years.
When you look at a 450,000-year record, and the last 100 years, or 150 years stands out like a sore thumb, there's not much question that we're involved in some way or another. And surely that's not surprising. I mean, we are such an incredibly powerful force on this planet, our species. I mean, most of the land area of the Earth that is habitable, that is cultivatable, we've cultivated or we've inhabited. We've moved mountains, we've redirected rivers, we've mined all this coal. We're a global force.
I have no doubt that an increase in carbon dioxide in the atmosphere should lead to some increase in global temperatures. The question is how much? And how can we be sure that any temperature increase that we do find in the record is in fact due to this additional carbon dioxide? Since we know that the climate also changes naturally, it warms, it cools, how can you distinguish a warming produced by an increase in carbon dioxide from a warming produced by some other cause, let's say by the sun?
The argument that fossil fuels are changing the climate has alarmed coal, gas, and oil producers. Because so much is at stake, the energy industry have been following the scientific arguments closely.
I understand that people get uneasy over the concept of more CO2 going in the air, but you can't live your life based on speculation. And we know today that using fossil fuels is a good thing. It leads to economic growth. It allows more people to live longer on Earth. There are positive goods that come from using fossil fuels. There's a speculative bad that people are holding out there saying, therefore, let's stop using fossil fuels. And I think that's an imprudent approach.
The coal industry has mounted an aggressive challenge to the whole idea of human-induced climate change. Its high-powered public relations campaign argues that CO2 has been unfairly characterized as a pollutant.
In the past, we've had these great struggles over pollution in the United States. Sulfur dioxide is a pollutant. NOx is a pollutant. Carbon dioxide is a benign gas required for life on Earth. It is not a pollutant. It is not regulated. There are no state laws dealing with CO2. There are no congressional laws that give an agency the right to regulate based on CO2.
Far from being a pollutant, the coal industry argues, CO2 is a powerful plant fertilizer. So producing more of it will green rather than pollute the planet. Its video, The Greening of Planet Earth, maintains that industrial CO2 will fertilize the Earth, and the enhanced forests will eventually soak up the excess greenhouse gas.
Grasses will grow where none grow now, and great tracts of barren land will be reclaimed.
It argues that horticulturalists pump CO2 into their greenhouses, 5 times current atmospheric levels, to make the flowers and vegetables grow faster. And indeed, the plants thrive. The industry believes that characterizing CO2 as a fertilizer rather than a pollutant turns the controversy on its head.
The only thing we are concerned about is carbon dioxide levels becoming too low. Because if carbon dioxide levels were to fall below, let's say, 1/2 of the present level, as they almost did during the last ice age, if they were to fall below 1/2 of the present level, then plants would be in real trouble. After all, carbon dioxide is plant food. Without carbon dioxide in the atmosphere, plants would disappear.
While it's accepted that CO2 is a plant fertilizer, it's not known just how the world's forests will react. Will they be able to keep up with ever-increasing CO2 emissions? In a remarkable series of federally funded experiments, scientists are trying to test the greening hypothesis. In 50 years, if current trends continue, CO2 concentrations will be double the pre-industrial level. And that's just what this forest is getting.
Our experiment is an attempt to grow an entire forest at 560 parts per million. In other words, we're replicating the growth of forests 50 years from now around the world, when all forests will be bathed in that atmosphere. We're essentially jetting CO2 into the forest.
Doing science on this scale is a massive undertaking.
Each of the experimental plots consists of a row of towers that inject carbon dioxide 24 hours a day, 365 days a year.
As the trees grow, carbon dioxide flows in and out of the forest. Some carbon getting locked up as wood, some decaying back into the atmosphere. So everything in this forest of the future must be carefully measured. Only 2 years into the experiment, the scientists can already see some changes.
As a result of the first 2 years of the experiment, 1997 and 1998 growing seasons, we found a 25% growth rate increase in the loblolly pine exposed to high carbon dioxide in the forest. Whether or not that continues is a real source of interest to us.
So is the coal industry right? Will this enhanced growth help suck up the excess CO2? Only, say scientists, if the CO2 stays out of the atmosphere.
A forest might sequester CO2 for 50 years, 100 years, and then at a certain point, it comes more or less into balance. because enough organic matter in the forest has been built up that decay starts to catch up with photosynthesis. If we chop down the old tree, we have to make sure that most of that tree is put into a usable product that has a long life. And what happens then? Eventually, the lumber rots or gets burned.
Eventually, within a century or less, the carbon locked in wood will find its way back into the atmosphere as CO2. And there's another reason for believing that plants alone can't absorb all the CO2, the vast size of the fossil fuel reserves.
When you look at the amount that is potentially available in coal, it's such an overwhelming amount. If you were to store all of that in plants, the terrestrial biosphere would be 4 or 5 times the mass that it is now. It's hard to conceive that how plants could keep this up, over centuries.
But even without the greening of planet Earth theory, the fossil industry is unwilling to concede that increased CO2 will translate into major climate change.
There are reasonable people that have speculative fears about more and more CO2 going into the air impacting climate. But there is no basis, no mechanism that anybody can point to or look at to say that more CO2 in the air is going to lead to catastrophic global warming or apocalyptic global warming as opposed to some mild warming, which is nothing to be concerned about at all.
It's not disputed that CO2 levels are a third higher today than before the Industrial Revolution, and will double and perhaps triple in the next 100 years. The real crux of the issue is how precisely this rapid rise will affect the Earth's climate, and whether those changes will be bad or good. The National Center for Atmospheric Research, NCAR in Boulder, Colorado, is one of the world's top centers for climatology. Inside, there are scientists whose job is far harder than any weather forecaster. They must try to predict the climate a century into the future.
So are you getting a stereo 3D
Tom
effect?
Wigley is one of NCAR's climatologists. Wearing special 3D goggles, Wigley and colleagues can look at models of possible future climates.
Cloud ice, and the colored surface in the center is a relative vorticity, and it's being colored by temperature. So we have an isosurface of vorticity and then temperature colored on top of it.
The pictures on the screen are conjured up by supercomputers. These high-tech crystal balls offer the only means of thinking through the climate consequences of a world in which CO2 levels are double or triple what they are today.
This one, I think it's 36 by 92.
A climate model starts by trying to capture all the many factors, natural and human, which can affect or force the climate system, either trapping or reflecting energy.
There are really 3 categories of factor that one has to consider. One is the influence of human activities, the buildup of carbon dioxide in the atmosphere and other greenhouse gases, and also the effect of sulfate aerosols. Aerosols are very small droplets that are primarily made of sulfuric acid or ammonium sulfate that are suspended in the air, and they arise from fossil fuel combustion, and those particles have a cooling effect. The next important issue is, what about natural external factors that might cause temperature to change on a global basis? We know from satellite measurements that the sun changes on a decadal timescale. The other external influence is the effect of volcanic eruptions, and a prime example there was Mount Pinatubo that erupted and caused, for a year or two, a substantial amount of cooling. In addition, there are other interactions that are going on purely internally within the climate system. As the amount of heat in the atmosphere is transferred to ice masses or to the ocean, that could cause, for example, the globe to warm by 1 or 2/10 of a degree or cool by 1 or 2/10 of a degree over a 100-year period.
The many processes which push and pull the climate system are fed into the supercomputers.
You can also see this kind of diurnal cycle.
Then things get even more complicated.
Between the day and night. It's a little more obvious.
The climate's ultimate response depends on a complicated chain of feedbacks
Better than a satellite, isn't it?
that can either amplify or diminish the original warming or cooling.
We're at the point now where the amount of carbon dioxide is roughly double the present level. And if we were to add carbon dioxide to the Earth's atmosphere and cause warming, then the oceans would warm and the amount of water evaporating from the oceans would increase. And it happens that water vapor is also a powerful greenhouse gas, so that by putting carbon dioxide into the atmosphere, we increase the amount of water vapor, and so we increase the total amount of greenhouse gases in the atmosphere and amplify the effect of carbon dioxide alone.
Here's a straightforward example. You first warm the climate for whatever reason, and then the chain is snow and ice melt, a darker surface is exposed, that darker surface absorbs more sunlight than did the snow and ice that was there before, and therefore the climate warms even more. It's a positive feedback. It's as though you had the thermostat in your house set so that when the house warmed up, it turned on the furnace and warmed it up still more.
But some feedbacks, like clouds, are even more complex.
If a low-level cloud is generated, then that shields the surface from the sun so that you get less solar radiation arriving at the Earth's surface. So that's a negative feedback. However, if you generate more high clouds, then those higher clouds can actually help to trap the infrared radiation leaving from the surface and warm up the system.
NCAR is just one of a dozen scientific groups who have tried to incorporate all these feedbacks into their computer models. Under pressure from policymakers, they have tried to predict what will happen to the Earth's climate when CO2 doubles in the atmosphere. All the models predict the Earth will warm. But the wide range of predicted temperature increases has drawn criticism from greenhouse skeptics.
These models are all produced by very competent people, excellent meteorologists, fantastic computers. Why do they not agree? Why do some models predict a warming for a doubling of CO2 of, let's say, 5 degrees centigrade, which is 8 degrees Fahrenheit, and why do other models predict something like 1 degree?
The different predictions reflect real gaps in knowledge about the Earth's climate. If the water vapor and cloud feedbacks are strongly positive, as some modelers assert, then a huge change of up to 8 degrees Fahrenheit is to be expected. If this feedback is weak, as some skeptics argue, then a rise of only a degree or so will occur.
If you didn't amplify what CO2 did with having water vapor and clouds go along with it, you'd only at most get a degree or so.
With a doubling?
With a doubling. And tripling would not do much more. And people have pretty much accepted this would not be a major change in the world as we know it.
The computer models tell of possible futures, some scary, some less so. Which is true? Currently, there's no way to know.
Computer models of climate are the most complicated, ingenious computer systems I've ever seen. I mean, they really are good. But in the end, you have to just face the fact that they are not going to be able to give you precise, certain answers. They're going to give you, we think this is what's going to happen, and here's the limits of error. And that's the uncertainty, and you have to choose.
If the scientists are uncertain about the precise global temperature increases, they know even less about the specific effects the warming will produce. Of greatest concern is sea level rise caused by melting glaciers and thermal expansion of warmer water. Coastal areas from Venice to California would then be vulnerable.
off the coast of California during El Nino events, the sea level rises. And in the last El Nino event, it was about 8 inches above the normal value. And what we saw was a lot of coastal erosion, houses toppling into the sea. And so that's sort of an indication as to what increases in sea level can do. We can adapt to a climate change as long as it occurs slowly enough. But if it occurs too rapidly, then it disrupts the assumptions that we've built into the way in which society works, whether we're planning agriculture, whether we're planning a building with its heating requirements, whether we're planning a dam.
If such human-induced climate effects occur, rich nations may be able to adapt and build seawalls. But for some countries, this isn't an option, like the 1,200 low-lying Maldive Islands isolated in the Indian Ocean.
All of these islands are totally flat. The average height above sea level is about 1 meter, and they are totally exposed to the sea. If there is even a minute change in the level of the sea, or a change in the size of the waves that come into our shores because of increased incidence of hurricanes, typhoons, we are all dead. The impact of global warming and climate change can effectively kill us off, make us refugees, lose every bit of land that we have available to us right now.
But greenhouse skeptics think such scenarios are alarmist. Modest warming, they argue, may even be good.
We have to ask, what are the impacts of a warmer climate? What is the impact on agriculture? The answer is, it's positive, it's good. What's the impact on forests of greater levels of CO2 and greater temperatures? It's good. What is the impact on water supplies? It's neutral. What is the impact on recreation? It's mixed. You get, on the one hand, perhaps less skiing. On the other hand, you get more sunshine and maybe better beach weather. Let's face it, people like warmer climates. There's a good reason why much of the US population is moving into the Sun Belt, and not just people who are retiring.
But most climate scientists are less optimistic.
We're talking about humans modifying the climate so that if we're lucky, we only get another degree in the next century. And it could be several degrees per century as our best guess. Compare that to the degree per millennium of history, and now ask one more factor. How are the species of trees, for example, and birds and so forth, how are they going to migrate? In history, they just migrated. Now they have to cross factories, farms, freeways, and urban settlements. So if you have the combination of fragmented habitats with nature getting into smaller and smaller patches, now you change the climate 10 times faster than the history for which they have experience, this seems to me an absolute prescription for an extinction crisis.
And some scientists caution there's a possibility that even modest warming might trigger major climatic changes by destabilizing the currents of the oceans. The oceans are the wild card in the climate system. By carrying warm water from the equator to the North Atlantic, currents like the Gulf Stream have a tremendous impact on the Earth's climate. By the time the Gulf Stream has reached the North Atlantic, the water has given up its heat. The now cold and salty water is so heavy it sinks to the bottom and returns to the equator to form a closed circulation.
These circulations are responsible for taking water from the top of the ocean down to deep levels in the ocean, in some cases right to the bottom. In doing so, in the present circumstances, this is a way of getting heat into the ocean and also a way of getting carbon dioxide buried in the deep ocean. So it's doubly important, this circulation, for the climate issue.
But for this, the climate in Europe would be very different.
Think of the climate in the British Isles or in southern Norway. It's a mild climate. You can play golf in Scotland in January. But what's the latitude of northern Scotland? I mean, bring it over to the United States and you're sitting in the middle of Hudson's Bay.
What worries some scientists is that in the past, this circulation appears to have stopped. A close examination of polar ice cores reveals about 10,000 years ago, while the Earth warmed up from the last ice age, the climate suddenly switched back into a cold state. Temperatures fell nearly 10 degrees in a decade. Some scientists believe it was caused when fresh water from melting glaciers flowed into the North Atlantic and disrupted the ocean circulation. What might happen if today's global warming caused the circulation to stop?
First, the North Atlantic would get much colder than it is today. That would mean northern Europe would cool down very rapidly. If that kept up over time, one would get more and more snowfall over time. And one of the hypotheses for going into an ice age is a shutdown of just that circulation, leading to more and more snowfall. Then it accumulates, it lasts over the summer, and steadily over hundreds, thousands of years, you can build up glaciers on land that was previously vegetation covered. Paradoxically, a warming in that case would be leading to a catastrophic cooling of some parts of the world.
The mighty oceans, some scientists argue, are the biggest uncertainty in the climate system, capable of dramatic climate surprises. After decades of research, climate scientists have presented many possible scenarios for the future of the planet. Because of uncertainties about effects of all the feedbacks involving atmosphere, ice caps, and oceans, they still can't say precisely what will happen.
I can imagine so-called feedback processes, where if you warm up the Earth, you melt snow and ice, which adds further warming. If you do that, it makes the clouds taller, which makes them trap more heat instead of wider. And if I conjure up these feedbacks, I can end up expecting that we could have climate change that's catastrophic in the next century. I can also conjure up another set of feedbacks. The clouds get wider, that it gets drier in between the clouds. There are a number of feedbacks we can conjure up, which makes it warm up only a degree or so at the relatively mild end of the spectrum. Well, most scientists would argue that this very mild and very catastrophic outcomes are plausible, maybe even a 10% chance of each of them. But the bulk of the likelihood is somewhere in between the end of the world and the good for you scenarios that you see all the time in the newspapers and in the congressional debates.
While scientists remain unsure of how the climate will change if CO2 continues to rise, they're certain we have already altered the composition of the atmosphere. Continued burning of fossil fuels now poses a credible threat to the climate. And since there are vast untapped supplies of fossil fuels in the Earth's crust just waiting to be exploited, today's greenhouse emissions might be eclipsed by what is to come.
If we burned all the coal in a couple hundred years, we would very likely increase the atmospheric CO2 concentration by more than a factor of 10. That's huge. There would be no debate about anthropogenic climate change, man-made climate change. It would be clear as a bell. Once we have driven up CO2 levels in the atmosphere, for it to come back down, it would take a very long time. My timescale for that is thousands of years.
If a skeptic says that he or she is not worried about doubling, ask them about tripling or quadrupling. And ask them about all the other gases besides carbon dioxide, some of which are increasing faster than CO2. There comes a point where you can't escape the idea that you're having serious climatic consequences. And so the issue becomes one of guessing whether we get wise before that day, or whether we have to wait for some perhaps quite unanticipated climate surprise that wakes us all up.
The emerging consensus among climate scientists that global warming was real became the fuel for a growing political movement to reduce greenhouse gas emissions. The White House was at the center of this movement. In October 1997, Clinton and Gore invited 110 TV meteorologists to a global warming briefing, hoping to recruit them as foot soldiers in the campaign.
We have to say there's a challenge out there. We have to respond to it. Here's the principles we want in our response, and then we have to get after it. But we can't do it until we build the awareness of the American people.
People who've been on the other
But the
side
White House point man on the issue, who had championed it for decades, is Vice President Gore.
This is coming, and we've got to do something about it. Are we going to be a part of the problem or a part of the solution? If we sit back and do nothing and allow this to happen without change, then what the mainstream scientists from every country in the world are telling us is that it's going to have profound changes in the pattern of climate.
Gore was trying to build public support because international negotiations about global warming had reached a critical stage. In December 1997, representatives from 160 countries met in Kyoto, Japan, to attempt to limit world greenhouse gas emissions. Environmental groups were out in force, hoping that this meeting would begin a radical transformation.
If we're going to solve the problem of global warming, the United States has got to be a world leader, just as we are on just about every other international issue. It's not a problem we're going to solve overnight, but what we can do is change the direction. Now, every year, emissions are higher than they were the year before. We've got to turn that around and get in a situation where gradually but steadily we're reducing our emissions of carbon pollution and other heat-trapping gases. I think we can do that.
The opportunity of Kyoto.
Out of this meeting, it was hoped, would come binding agreements to limit greenhouse gas emissions.
We know what we must do. We know it can only be done together. So let us get on.
The fundamental issue at stake was the world's use of fossil energy.
Kyoto Protocol that we can show.
Because the United States uses more energy than any other nation, it would come under the greatest scrutiny. More than any other country, the U.S. is accustomed to cheap energy on demand.
We are criticized for being the highest per capita consumers of fossil fuels in the world. It's a positive good. There's a correlation between our energy consumption and our success. We don't succeed in the United States in spite of energy consumption. We succeed in the United States because of energy consumption.
Americans use 1/4 of the world's energy. A vast infrastructure delivers energy whenever and wherever it's needed. It works so seamlessly that Americans have stopped thinking about where energy comes from. Most of it, in fact, comes from burning fossil fuels. Every time we turn on a light, the odds are that the energy comes from burning coal. Close to 60% of all U.S. electricity comes from coal, so power stations must be supplied 365 days a year with this most abundant fossil fuel.
People don't think a lot about coal, and they're not required to think about coal, but coal in the United States is the major driver of our economy in that it supplies 56% of electricity. One 1,500 megawatt coal unit supplies electricity for 1.5 million people.
Coal generation is supplemented with other carbon-emitting fossil fuels like oil and natural gas. Some sources of electricity produce no greenhouse gases. Hydroelectric power, solar energy, the power of the wind, and the largest carbon-free source of energy, nuclear power, which currently supplies over 20% of U.S. electricity. All of these sources flow into electricity grids like this one, managed by Northern States Power in Minneapolis.
Scattered outages, there's
Let's see if there's any multiples in the west area now. I think
What few people realize is how much energy is being consumed 24 hours a day.
a lot of single.
That ticket was 32684.
It's 10117.
7530 Central.
Even at 3 in the morning, 55% of the load is operating.
Nothing totally shuts down. I mean, even at 3 o'clock, you have street lights on. You have factories that are working on a 24-hour period. And what we'll do at the nighttime is run our cheapest units, our coal and our nuclear units. And those are the units that we call our baseload units that we use all the time, and they produce the lowest cost energy. About 7 o'clock, our load will start to pick up as people get up and go to work and buildings start opening up and air conditioners go on. What we'll do is turn on different generating plants as demand increases.
All over America, the scene is the same. As the day gets going, the demand for energy ramps up. And since most of this energy comes from fossil fuel, it all adds greenhouse gases to the atmosphere. Take the simple act of making toast. Over the course of a year, a toaster, on average, consumes about 39 kilowatt hours of electricity. And each one of those kilowatt hours sends about a half a pound of carbon into the air.
When you multiply that out, what you get is about 8 kilograms of carbon per year for toasting bread every day. And if we convert it to pounds, by multiplying by 2.2, we get about 20. 20 pounds of carbon per year associated with using a toaster.
Or consider central air conditioning.
Typical home in the South would use about 4,000 kilowatt hours for air conditioning. If we convert that to carbon emitted, we get about 800 kilograms of carbon emitted per year from central air conditioner, and that's about 1,800 pounds, which is more than the weight of a small car like a Toyota Corolla.
Since each pound of carbon entering the atmosphere combines with oxygen to form nearly 4 pounds of carbon dioxide, America's contribution to greenhouse gas buildup is even more striking. Taking a shower each morning produces 550 pounds of CO2 in a year. Using a computer 40 hours a week produces 600 pounds of CO2. Lighting an average house for a year emits 2,000 pounds. Lighting a large office building, not surprisingly, produces much more, 2.5 million pounds of CO2. And about 1/3 of all American greenhouse emissions come from automobiles.
People drive on average about 12,000 miles per year. And a typical new car gets roughly 28 miles per gallon. That means that you will use about 430 gallons per year. And so over the course of the year, the person driving this new car will emit roughly 2,200 pounds of carbon per year. That's roughly the weight of the car itself. Now, if you have an SUV which gets only 14 miles per gallon, you're emitting 4,400 pounds per year. It's essentially the same as having 2 cars on the road instead of 1.
1619, St. Louis Park, 5.
Apart from the energy we use to live, enormous amounts of power are required to manufacture all the things we buy. Grady Foundries in Minnesota needs as much electricity as a small town. And it needs this power on demand.
Grady makes all steel and iron parts. We make the rear end for the Dodge pickup trucks, and we make approximately 3,200 of those a day. We also make a powertrain component for the GM vehicles, and we make about 10,000 of those a day. If we lose electricity, we're dead in the water and we can't do anything.
On any given day, Minneapolis-based Northern States Power directs up to 8 billion watts of power to homes and businesses. It's the same in most U.S. cities. Because of this energy consumption, each American, on average, directly or indirectly, puts over 20 tons of CO2 into the air each year. Collectively, 1/4 of the world total. The energy use of industrialized nations like the U.S. is responsible for the dramatic 1/3 increase of CO2 in the atmosphere. But that's nothing compared with what is to come. The future of global warming will be determined by what happens in the developing world. Nations like Brazil, India, and China, where 3/4 of the world's people live.
In the developing world, you have both higher rates of population growth and higher rates of economic growth, which means that they have a huge potential growth in greenhouse emissions as they develop their electric power systems, their transportation systems, and the like. If you're living in a hot Chinese city, first you want a television set, and then you want a fan, and then you want an air conditioner as you get more wealthy. And you would don't do that, I would want to do that. And once you have an air conditioner and a television set, then you'd like to have a car. And it's going to be very difficult for those countries to take a path that is dramatically different from the one we took.
In India, each person currently produces only 1/40th as much CO2 as an American. But India's population is so large and its growth so rapid that it will soon surpass the U.S. in greenhouse emissions.
The country today has about 1 billion people, and it's growing. In fact, the expectation is by about the middle of the next century, India would have the largest population of any country in the world, larger than China. We must remember that this is still a very, very poor country. You're talking about people essentially earning $1 a day. And given the fact that 70% of our population lives in rural areas, we have a long way to go.
India has aspirations. Indians like Mr. Audia want their children to have the possibility to leave the villages. Over the next century, India plans to transform itself from a largely rural agricultural society into an industrial powerhouse. And the energy driving that transformation will come largely from fossil fuels. In countries like India and China, mainly coal.
Even to produce the basics of life, whether it's food or steel or automobiles, whatever, you need large factories. And those large factories need large power plants. They would need large refineries and the like. And you know, those are things that we can't get away from. They have to grow if this country has to get rid of poverty.
If rapidly growing developing countries like India simply follow in the footsteps of the West, greenhouse emissions will soar as their populations and energy consumption increase. To solve the global warming problem, therefore, would clearly require the cooperation of the developing world.
What if the developing countries did not take part and we wanted to achieve this target of twice pre-industrial levels? Then it would require the rich countries to have negative emissions by about the year 2045 or 2050. In other words, they would have to be pulling carbon dioxide out of the atmosphere to make up for the growth in carbon dioxide emissions in the developing world.
Back at Kyoto, confronting these issues polarized the conference, pitting rich nations against poor.
Here in Kyoto, we have put forward the notion of very ambitious targets.
What was being negotiated was nothing less than a greenhouse gas allowance for each country, which they could not exceed. But the developing nations argued that since they didn't create the problem, they should be exempt.
It's essential that the developed countries take the first steps. They consume huge quantities of energy. They have the technological and financial resources to start doing something about this problem. This is the kind of leadership one expects the most powerful country in the world to show.
I'm afraid we are running out of time.
They don't want to do anything unless we go first. They didn't create the problem. They're poor, we're rich. The gases that are up there are not their gases, they're our gases. But it is also reasonable for us to say, hey, wait a minute, it doesn't help for us to do this unless we have some kind of an agreement with you that when you get to particular levels of income and ability, you will also join in.
We are here, the political leaders, to help our negotiators.
The arguments went on for days. As time started running out, it began to look like there would be no agreement.
A viable and significant agreement. We are not here.
Still missing from the negotiations was global warming's greatest champion, Vice President Gore.
Well, there was a real question of whether Al Gore should go or not, because there was a sense that this whole thing could collapse. Some of his advisors were saying, don't go. Yet on the other hand, if he hadn't gone, it might have looked like he was scared or shirking an issue that he's talked about throughout his career.
At the last minute, Gore arrived to try and broker a deal. After a day of intense negotiations, Gore managed to keep the Kyoto Protocol from collapsing, and in an uncompromising speech, he reminded the delegates of what he believed was at stake.
The human consequences and the economic costs of failing to act are unthinkable. More record floods and droughts, diseases and pests spreading to new areas, crop failures and famines, melting glaciers, stronger storms, and rising seas. Our first step should be to set realistic and achievable binding emissions limits. For our part, the United States remains firmly committed to a strong, binding target that will reduce our own emissions by nearly 30% from what they would otherwise be. A commitment as strong or stronger than any we have heard here from any country. The imperative here is to do what we promise rather than to promise what we cannot do. For example, in my country, we remember that...
But in brokering the Kyoto Treaty, Gore had agreed to let the developing nations off the hook. They made no binding commitments to reduce greenhouse gases. Most developed nations, however, committed to binding cutbacks, with the U.S. agreeing to roll back greenhouse emissions to 7% below what they were in 1990, about 20% below what they are today. Reaction in the U.S. was swift.
What the long-term goal of the Vice President of the United States is to ultimately eliminate all fossil fuel use in the United States. President Clinton, in connection with Kyoto, said it was, his words, a good first step. A first step to what? A first step to eliminating fossil fuel utilization in the United States.
As Gore left for home, he knew he faced a hard fight on Capitol Hill. The Senate, who would have to ratify the controversial treaty, were far from happy with the deal.
My problem with Kyoto is there's no net gain. In other words, if you allow the developing nations to have a free ride, and if you buy their argument, well, they deserve a chance to catch up as the industrialized nations have advanced, then when we're through, have we got any significant net gain? Have we reduced emissions?
Ironically, most climate scientists were also underwhelmed by the Kyoto Treaty.
If everybody were to come on board with the Kyoto Protocol, then that would slow down the rate of climate change by a very, very small amount. As a best guess, we think that the concentration of carbon dioxide in the year 2100 would be about 700 parts per million, which is roughly double what it is today. If we enact and follow the Kyoto Protocol, then we might reduce the build-up by a few tens of parts per million carbon dioxide. In other words, instead of doubling the amount of carbon dioxide, we might only increase it by 90%.
Computer models show that the provisions of the Kyoto Treaty would not stop the rise in atmospheric concentrations. To do this means eventually going way beyond Kyoto and cutting world fossil emissions by a half or more. How could this be done? Scientists and environmentalists could imagine a whole range of potential solutions, from developing alternative energy sources to expanding nuclear power, to simply increasing energy efficiency.
The first major thing to do is to get efficiency improved. We are not anywhere near as efficient as we could be. We don't all have the best motors, the best light bulbs, the most efficient cars and industrial processes. We're not perfect. And therefore, if climate policy forced us to be more efficient, we actually would be replacing inefficient technologies with more efficient ones that would cost us less money to buy them than the money we're saving in fuels.
A lot of energy is simply wasted. If we made our energy go further, we would need less, and therefore emit less greenhouse gas.
Important distinction to make in dealing with any of these issues is that there's energy conservation, which is typically defined as deep deprivation, essentially putting on a sweater, dealing with discomfort in some way. And then there's energy efficiency, using new technologies to do the same thing with less energy.
Many electronic devices leak energy. Televisions are a prime example. When they operate, they draw about 100 watts of power. But even after they are turned off, they may still draw energy.
And some of my folks actually went to Circuit City and measured all the TVs there. And what they found was a huge range in the standby power of these devices. And some of them, not just televisions, but other kinds of appliances, were leaking as much as 20 to 25 watts. And you found other televisions that were less than 2 watts. And there was no difference in price for these devices. It was just that the manufacturers hadn't really thought about it for a long time.
But as even proponents of energy efficiency admit, human behavior seems to be moving in the other direction. Americans are buying larger homes and larger vehicles.
We're buying larger, heavier vehicles, so the average weight and size has gone up. The engines and transmissions we use have got a little more efficient, and the two things are roughly canceling out. So the technology is getting more efficient, but the miles per gallon aren't getting better because we're steadily buying larger and heavier vehicles. So we have this choice. We could drive smaller vehicles and they would use less fuel and put less CO2 into the atmosphere. But that's not our current choice.
But perhaps the biggest barrier to reducing greenhouse gases is economic growth. American industry uses energy more efficiently than at any time in history. The Anderson Window Company, which makes the top-of-the-line energy-efficient window, is no exception. But ironically, because business is booming, they use more energy than ever before. Because of the economic boom of the 1990s, America enters the new millennium nearly 20% above its Kyoto target.
In the next 20 years, the nation's electricity requirements will be increased by 60%. We'll go from 3 trillion kilowatt hours presently to about 4.6 trillion kilowatt hours in 2020.
You're talking about America?
That's the United States.
Why does a rich country like America need to consume more energy?
It is a matter of all of the things that you and I see around us. A computer on the internet uses 1 kilowatt per hour in use. And you think about the explosion of all of those computers, not only in this country, but in modernized and developing countries around the world, you begin to get an idea of what tomorrow looks like.
The total energy consumption of all of humankind at this point in time is about 10 terawatts. That's 10 trillion watts. That's the rate at which primary energy is used. That's the rate at which we're burning gas and oil and coal. That's 10 trillion watts. The projections, the so-called business as usual projection, is that over the next 100 years, the demand for energy will increase roughly by a factor of 4.
These projections reveal just how stark the problem really is. The world must somehow stabilize greenhouse gas emissions in the atmosphere at the same time as it is planning to triple, even quadruple, its energy use. By 2100, the world that these children's children will inhabit may need 30 or 40 trillion watts. And to prevent massive greenhouse buildup, most of this must be carbon-free.
The magnitude of the job is massive. If you confront the problem honestly, I mean, if you really look at the problem and you say, what I want to do is I want to stabilize the amount of carbon dioxide in the atmosphere at some level twice the pre-industrial level of CO2. It's almost impossible to do that unless there's a truly massive transition in the global energy system away from fossil fuels. That is the bitter pill at the bottom of all of these discussions.
If America consumes ever larger amounts of energy, and if the developing nations follow in its footsteps, then the world must, sooner or later, confront an awesome challenge: to find a carbon-free replacement for fossil fuels. Where will this energy come from? Some say the technology has already been invented: renewable energy. Solar power, the energy of the wind, and biomass, the growing of vegetable matter to use for fuel.
I think it is very credible that over a longer period of time we can get the majority of our electricity from new renewable energy sources.
Others argue that what we need is an expansion of nuclear energy, which also produces no greenhouse gases. But environmental groups do not want carbon-free energy at that price.
Nuclear energy has no role in this debate. We have no safe way of putting away radioactive waste. There are cleaner alternatives, and Greenpeace firmly disagrees with the use of nuclear power.
Hydroelectric power has also recently come under attack.
Large-scale hydropower has been very disruptive in our rivers, specifically in the Pacific Northwest. We want to put an end to hydropower, and cleaner energy solutions are there: solar and wind power.
So you don't want coal, you don't want nuclear, you don't want hydro.
Right.
So what's left?
Renewable energy technologies.
In recent decades, great strides have been made to develop sources like wind power. Buffalo Ridge in North Dakota is one of the windiest locations in the United States. This wind farm has been sending electricity to the Minneapolis grid for over 2 years now.
Southwestern Minnesota has some of the best wind characteristics of any site in the United States. The problem with wind is that the wind on the average only blows 25% of the time, and it blows the strongest in the spring and the fall when our loads are the lowest. At our peak times in the peak summer, peak winter, it generally, a lot of times, produces zero. We can't count on it being there. We have to wait for the wind. If the wind's there, great. If it isn't, then we'll have to open the throttles on something else.
They're not going to all be in one place. They're going to be spread around. So the wind may not blow in North Dakota, but it'll blow in Northern California. And that will start to become predictable as the utilities get more experience with it.
The experts that we've been working with have quoted that South Dakota, North Dakota, and Texas have enough wind power annually to meet the United States electricity demands. Now, if the wind stops blowing, then we would have, backup resources, solar energy.
In business for 15 years, Sunray in Southern California is one of the longest-running solar plants in the world. Its 30-acre field of mirrors captures the energy of the sun and turns it into electricity without emitting greenhouse gases. But it can only generate power when the sun shines.
The coal plant can generate year-round, 24 hours a day. To where here, we can just kind of run when the sun's out, which is out quite a bit. We get about 265 days of sunshine here. But if you get any kind of high stratus clouds or anything like that, you'll see your power just go right off the grid.
When the sun's out, Sunray produces 30 megawatts of electricity. While impressive, it can't yet compete with the coal plant next door, which produces nearly 800 megawatts, 24 hours a day, 365 days a year, for a quarter of the cost. Solar power has shown that it can play a valuable role in specific locations where the sun is plentiful, especially in the developing world in areas remote from the electrical grid. The issue is whether renewables can be scaled up to generate the massive amounts of energy that coal and nuclear do. Whether they can one day produce the trillions of watts the world's cities need. Whether they can ever replace fossil fuels.
Most people want to turn on the lights at night, and the sun isn't shining at night. Renewables tend to be very episodic, that is, they're not always there. And the power density is low. That is, the number of watts per square meter is pretty low.
And this may be a crucial weakness. Because the energy density of solar, wind, and biomass is low, very large areas of land will be needed to produce significant amounts of power.
There's going to be a certain inevitable amount of land use issues associated with renewable energy, in that you're going to need a lot of area. If you wanted to supply 10 terawatts of power, and you wanted to do it with biomass energy, you would need an area of the Earth equal approximately to 10% of the Earth's surface, land surface area. And that's a huge amount of land. That's all the land that's used in human agriculture right now. Now, if you needed 30 terawatts and you wanted to do it with biomass, you would need 3 times as much. So you could sort of imagine a world where the only things on the planet would be human beings and wheat. And we would eat the wheat and we would use the wheat to make alcohol for our vehicles, but there wouldn't be any other biological diversity because we would have appropriated all of the land surfaces to do that. That's the kind of issue that you have to deal with when you seriously talk about stabilizing CO2 in the atmosphere.
Land use and siting issues have even tempered some environmental groups' enthusiasm for wind energy. Recently, the National Audubon Society opposed the expansion of wind farms in certain parts of Southern California because of threats to bird populations.
Greenpeace would not want to see, every bit of open space covered with windmills. That's not the issue, and that's not the case that needs to be. The effects of building wind farms on our land compared to drilling in our oceans for oil or taking off mountaintops for coal is nothing compared to building wind farms or looking at solar plants.
The challenge of replacing fossil fuels in power stations is hard enough, but roughly a third of fossil emissions come from our vehicles. Because every gallon of gas releases 20 pounds of CO2, engineers have looked for alternatives to petroleum. Some manufacturers imagine one day cars might work like this model and run on hydrogen. Instead of an internal combustion engine, this car uses a fuel cell, a kind of battery which combines hydrogen with oxygen to make electricity. The waste product is simply water. Prototype vehicles already exist which can run on hydrogen. The challenge to this vision of the future is where exactly will we find the hydrogen?
Well, petroleum comes out of the ground, coal comes out of the ground, natural gas comes out of the ground. It's down in the ground and we bring it out and use it. There's no hydrogen stored in the ground. We have to make it.
The good news is that you can extract hydrogen from natural gas. The bad news is that CO2 is released in the process.
So if you take natural gas and produce hydrogen, you've taken the hydrogens from the natural gas, the hydrogen atoms, but the carbon atom is going to come off as CO2.
To mitigate the greenhouse gas problem, the hydrogen would need to be made not from fossil fuels, but by splitting water molecules, using carbon-free energy. And it's hard to see how renewable sources like solar and wind can do this on the scale required, especially if they're expected to generate the world's electricity at the same time.
We need to think of the renewables as nice augmentations. They're not going to fill the great demand. The sensible thing to be doing now is to broaden all of the energy options that we have. We need to look much more carefully at nuclear as a serious option going into the future.
While enthusiasts once dreamed nuclear energy would run the world, no new plants have been built in the U.S. since the 70s. Plagued with controversy, many of the nation's plants will be decommissioned in the next 20 years. But given the grim realities of greenhouse gas buildup, some climate scientists are saying we should give nuclear another chance.
I think that the mistake that we've made is, again, we've made an irrational choice. The public has decided that nuclear power is somehow or other dangerous, and more dangerous compared to other forms of energy that we use. They're confused about the differences between generating electricity with nuclear power as compared to building bombs and killing people with nuclear energy.
But even assuming public fears could be erased, could a greatly expanded nuclear program replace fossil fuels? Nuclear reactors use uranium, a naturally occurring metal. How long would current reserves last if they had to run the world at the current rate of 10 trillion watts?
You only have about 10 years of U-235 power from all of the cost-effective uranium reserves. Even if you look at reserves which are more expensive now, and by this time the nuclear power would be getting considerably more expensive, you might have 30 or 40 years at 10 terawatts. And what if we need 20 or 30 or 40 terawatts for 100 years? Now you're done.
Conventional reactors cannot solve the problem. But there is one possibility. Breeder reactors, which turn a more abundant form of uranium into plutonium, can potentially extend nuclear's lifespan as a fuel source for hundreds of years. But breeders are a very complex technology, and because they produce plutonium, they raise serious issues about nuclear proliferation. So today, virtually no research is being done.
A high priority, and one that's now not being followed in the United States, is to find a socially acceptable version of nuclear power. I think one of the great tragedies of the current R&D, it's not a tragedy necessarily we're not building more nuclear power, because there are a lot of social reasons to worry about nuclear power. The problem is we're not doing the research that would be needed to search for a nuclear power option that would be socially acceptable.
Today, there is no known energy technology capable of delivering the amounts of carbon-free energy to stabilize greenhouse gases in the atmosphere. The most commonly cited cures for global warming, efficiency improvements, renewable energy, and nuclear power, appear not to be up to the challenge. But not everyone's demoralized.
Try to imagine what the world was like in 1899 compared to today, and what the technologies were that were being envisioned by even scientists and engineers, and what actually happened. They missed the movies, they missed airplanes, they missed automobiles, they certainly missed space travel and nuclear power and radar and lasers. And so there's really an issue of sort of timidity in are in the way that we've been projecting the technologies that might mitigate the fossil fuel greenhouse effect.
Harford argues that many of today's energy technologies, like nuclear and solar, came out of government-funded military and space research. So perhaps we need a Manhattan Project to find the technologies to combat global warming. Technologies which might capture the sun's energy in space and beam it to Earth. Technologies like nuclear fusion, offering limitless carbon-free energy. Even technologies which extract the carbon from burning fossil fuels and sequester it back into the ground. And other technologies which today are simply unimaginable.
But we haven't been doing any serious research on this problem. When I say this problem, on the problem of how do we power the world on a long-term basis with carbon-free energy.
If the technological obstacles to combating greenhouse gases seem difficult, the political challenges might be even greater. Even before the Kyoto Conference started, the idea of U.S. cutbacks was in trouble in the Senate.
It is the developing nations that will be the biggest emitters of greenhouse gases during the next 25 years. It is complete folly to exclude them from legally binding emission mandates. How could any treaty aimed at reducing global emissions of greenhouse gases be at all effective when it excludes these 130 nations?
Remarkably, even liberal senators concerned about global warming had concluded that voting for Kyoto was political suicide.
The fact is, our country can control global warming without causing an economic meltdown. Now, there are really three approaches.
You can't underestimate the power of the interests on Capitol Hill that are opposed to this, between the business interests and the labor interests and so forth.
Mr. Wellstone, aye.
Even Republicans these days are much more apt to call themselves green and to say they're fighting for environmental issues, but they'll only go so far, because you don't want to run into danger with the business groups that are crucial to funding a lot of these campaigns.
In a rare display of unity, the Senate voted 95-0, declaring their opposition to Kyoto.
Virginia, the ayes are 95 and the nays are 0, and the resolution is approved.
Climate scientists who had seen the treaty as a small first step were stunned.
I can't imagine that 95 United States senators believe that a rich country like the United States should take no leadership role unless poor countries like India and China have taken equal responsibility. I can't believe that 95 United States senators really believe that. I mean, if you believe that, then you would have to say that, that we have embarked on an incredibly selfish view of leadership.
In the 2 years since Kyoto, nothing has happened. Facing certain defeat, the White House has not even submitted the treaty to the Senate for ratification.
There's no chance of Kyoto being ratified. We are not going to do it as a society. The notion of reducing carbon dioxide emission levels in the United States 7% below 1990 levels by the year 2010 is a complete fantasy.
While the Senate and the White House are stalemated, what do the American people think? And what do they know about global warming?
People in general tend to know relatively little about this question. They know that auto emissions or coal emissions generate greenhouse gas in fairly large percentages, but there's an enormous amount of confusion as well. Our own studies have shown that 50% of the populace approximately would attribute some global warming cost to nuclear energy, for example, which is a kind of a scary finding in this particular context.
So whatever's going to happen because of our orbital position around the sun and the sun.
Hank Jenkins Smith is a political scientist who studies public opinion on environmental issues.
We don't have a chance.
If you ask people in general, what do most scientists believe? Majorities get it right. On the other hand, it doesn't take much to upset it. One or two cogent arguments about the problems with the science associated with climate change is enough to create substantial skepticism.
There's so much range in the natural fluctuations of all of the attributes of the Earth that I don't think they can get a computer model to handle all of it.
You know, you can't predict what's going to happen, you know, the climate. Nobody can. That's my opinion, you know. It's like they say one thing one day and the next day something else happens.
The Iraq War, with the oil wells burning out of control, they were telling us we're going to have a nuclear winter because of all of the soot.
It appears that it's going to take some convincing to get people to believe that this is a serious issue to which they should devote some attention, let alone resources.
What, are you kidding?
Suppose that you were able to vote on a national referendum to impose a tax on, let's just to keep it simple, let's put it on gasoline, which would put money into a fund to study this question. Would any of you vote for that kind of a referendum?
Absolutely not.
You wouldn't vote for it at any price.
I would want to know why the average consumer was being asked to pay for that. Yeah. I mean, that would be my question. Is this the only place that this funding can come from? Because I think it's a question we need to answer, but do we need to pay for it?
Mm-hmm.
For a mother with 4 children, 50 cents, you know, or even anything on a dollar adds up really quickly.
And then you don't really know if it would get used on that.
Exactly. Right. You're kind of skeptical as to where it's going to be used.
Okay.
The argument that the rich nations should take the first step had not swayed the U.S. Senate. Does it resonate any better with the average U.S. voter?
Doesn't seem to. First off, remember that people can quickly retreat to the idea that, well, we don't really know that it's that bad. And as long as they can retreat there, then you don't have much moral point. You can make a moral point if they begin to accept that these things are in fact having these potentially harmful effects. And we're just not there yet.
During the presidential primary campaign, some observers began to wonder whether even global warming's most ardent advocate was backing off the issue. In his presidential announcement speech, for example, Gore uttered only one brief sentence about global warming.
He hasn't really talked about it hardly at all since Kyoto. There's some talk that his advisors fear it's a no-win issue politically. This is a practical reality of running for president. When you're a lone U.S. senator writing a book, you can do more what you want and say what you want and say, this is what I'm fighting for, we got to have it, win or lose, this is what I want. But when you're in a position where you can make things happen, when the spotlight is on you, when you want to be the next president of the United States, you have to be a lot more careful.
Then, just last week, Gore suddenly seemed to openly embrace global warming once again, reissuing his controversial 1992 book on the subject and saying we must now take urgent action. At Mauna Loa in Hawaii, scientists continue measuring the greenhouse gas buildup in the atmosphere. Most climate scientists are now resigned that Kyoto has failed. One thing, however, is certain. The amount of CO2 entering the atmosphere will continue to rise, and in time, the impact on the climate will become clear.
What we're afraid of is that if the planet warms too much, we're going into unknown territory. If we were to warm the world by 5 degrees, then I strongly believe that large parts of the Antarctic ice sheet would flow into the ocean and melt and cause sea level to rise by many meters.
Beyond sea level rise, many other serious effects may occur. Increased frequency of intense storms, the spread of infectious diseases throughout the world, major droughts, crop failures, and famines, the destruction of species and habitats. All these things are possible. but it's equally likely that change will be more modest.
I certainly think 50 years from now, we will be seeing clear evidence of human climate change. We will have a better knowledge of where it is in this range that we've been talking about as to whether it's going to be huge or smaller. Whether we will have clear evidence 20 years from now is not so clear to me. I think there will still be substantial arguments. There will still be people who will argue that this is natural variability for one reason or another. But gradually, with time, I think people will recognize that something weird is going on with the weather, and maybe we should do something about it.
It is distant, and for that reason, difficult, but it's not so distant. If I have a grandchild today, my grandchild born today will not be as old as I am until 2062. It's not that far away in terms of generations of people that are around. So you can care about this issue because of people you know.
We're in the fossil fuel era of human history. If humankind is going to have a future on this planet, it is absolutely inevitable that we're going to have to find another energy source. The thing that's happening to us now is that we have to make that decision in the 21st century, whereas we may have been able to postpone it to the 22nd century, if not for the greenhouse effect.
I think this is a very difficult problem. And I wouldn't bet we can solve it. I think it is extremely difficult. But it's worth our effort to really work hard to try to find a way to solve it. Because the potential is that we're changing the face of the earth for all future generations.
For more on the climate and where we might be headed, visit our website. Examine the debate over the new consensus on warming. Tally your own carbon energy use. See how ice cores are a history book on key climactic events. Check out radical ideas to combat global warming. Access a teacher's guide and join the discussion at pbs.org or America Online keyword PBS.
Sometimes in great detail. And these records are now being scrutinized by climate historians.
Weather was an extremely important variable in daily life, and most people worked outdoors, and they were outdoors for most of the day. They were much more vulnerable and they knew it. And for this reason, there was an extreme interest in any kind of predictions.
Throughout history, there have been people who documented events regularly and meticulously. physicians, artisans, and the monks here at Einsiedeln in Switzerland. They recorded the time the cherry blossom appeared, the freezing and thawing of lakes, the state of the wine harvest.
For instance, a very early cherry blossom is always related to a very warm month of March. If the Lake of Zurich is completely frozen, we know that it's equivalent to 2 extremely cold months, always, because we know it from the period when we have both the observations and the measurements.
From these diverse records, climate historians can glean a lot about the past climate. By combining data from many sites, this clever forensic work can yield a detailed picture of areas like Central Europe going back more than 1,000 years. Has Pfister found any period in the past as warm as the 1980s and 90s?
We had other periods which was also very warm, but it was equivalent to the 20th century prior to 1988, I would say. This was a period of warm climate, but I would say it was a period of warm natural climate. To the period between 1988 and 1997, there is absolutely no equivalent as far as I can look back.
But this technique too is limited. Only a few areas like Europe have long-term records which survive. To get a handle on the global climate, scientists have been forced to go beyond human accounts of the weather. "500 miles from the North Pole, a frozen lake will be home to a team of scientists for the next few weeks. It's part of an international effort to try and reconstruct the climates of the past.
We're here in the Canadian High Arctic on Ellesmere Island, about 500 miles from the North Pole. And it might seem strange that we would come to this kind of environment to study the problem of global warming. But what we need to do is to try to reconstruct the longer-term history of climate. And we do that by using so-called natural archives of climate, things that in some way retain in their structure a measure of how the climate has varied in the past.
Bradley and his team will spend the brief Arctic summer drilling through the ice and sampling the pristine sediments at the bottom of Lake Tuborg.
Because the lake is frozen over for most of the winter, what we have is a
From record heat to raging storms, something strange is happening with the weather.
Global warming is real.
Or is it?
There is no basis to say that more CO2 in the air is going to lead to catastrophic global warming.
But what do we really know about the greenhouse effect?
You're dealing with something where there's legitimate uncertainty in science.
Is there a real solution to our dependency on fossil fuels?
If humankind is going to have a future on this planet, it is absolutely inevitable that we're going to have to find another energy source.
And does America and the world have the political will to tackle what could become the most troubling issue of the 21st century?
The notion of reducing carbon dioxide emission levels by the year 2010 is a complete fantasy. We are not going to do it as a society.
Tonight, PBS's premier science and investigative series join forces to investigate the truth about global warming.
Funding for NOVA and Frontline is provided by contributions to your PBS stations from viewers like you. Thank you.
For most of history, humans believed that the weather was governed by forces outside their control. But today, we're no longer so sure. Something weird, it's claimed, is going on with the weather. From storms and hurricanes to droughts.
Withering heat waves in Texas and in Florida. Cities that are setting 1,000-year records for high temperatures. How much more proof do we need that global warming is real?
And the future, some argue, could be apocalyptic, as ice caps melt and sea levels rise as much as 20 feet.
Over the last few years, you begin to get increased probability of extreme events. You're beginning to get a sense that these things are happening more than they used to. And people are beginning to connect that with global warming.
Vice President Gore is so convinced humans are warming the planet, he advocated an international treaty committing America to drastically reduce emissions from oil, gas, and coal. Burning these fossil fuels, he argues, puts greenhouse gases into the atmosphere, which trap heat and warm the globe. His opponents object that the risks are exaggerated, and any attempt to limit or get rid of oil, gas, and coal, which provide 90% of our energy, will cause an economic apocalypse, from job losses to recession.
This is the United States government identifying with a policy that would be devastating. What the long-term goal of the Vice President of the United States is to ultimately eliminate all fossil fuel use in the United States. That is their goal.
At the heart of this contentious issue is a battle for the truth. When we strip away the rhetoric and politics, what does science really know about global warming? The question has pushed the once obscure science of climatology into the spotlight.
Okay.
But the climate system has turned out to be very complex.
Spectacular.
The Earth is a big place. 3/4 of it is covered by water. There are giant ice caps, and deserts and mountains. But climate scientists somehow need to take the Earth's global temperature. Today, the Earth's weather is measured daily all over the globe by an international network of stations on land and sea, which report temperature, pressure, rainfall, humidity, and a host of other variables. Such global measurements are the prime database for climatology. Millions and millions of figures have been collated, corrected, adjusted, and synthesized. The problem is these measurements have only been taken systematically for a century. When averaged, a pattern emerges. During the past 100 years, the global surface temperature has risen by 1 degree Fahrenheit, or about ½ degree Celsius. This is a temperature record of the entire Earth's surface, not just the weather in one place. But is a 1 degree rise over a century a little or a lot?
What's really remarkable about the warming over the last century is both its magnitude, in terms of ½ degree Celsius, and its fact that it's been almost worldwide. Almost every site you look at has warmed dramatically since the middle of the last century.
But not everyone's convinced this is evidence that humans are warming the globe. Fred Singer, an atmospheric physicist, is one of a small band of scientists who have become known as greenhouse skeptics. He argues that the 100-year record is not what it appears to be.
The data are ambiguous. For example, the data show that the climate warmed between 1900 and 1940, long before humanity used much energy. But then the climate cooled between 1940 and 1975.
Only in the last few decades do rising global temperatures seem to coincide with the greenhouse gases we put into the atmosphere. Skeptics like Singer have also argued that long before the Industrial Revolution, the climate warmed naturally. For example, records show that in the Middle Ages, parts of the world like Greenland were warmer than today. The Vikings built settlements there and farmed the land.
The Vikings were able to grow crops, and life was good in Europe. Cathedrals were being built. There was plenty of food. Climate change is a natural phenomenon. Climate keeps changing all the time. It's either warming or cooling.
But records of one place, like Greenland, during one time, the Middle Ages, may not prove anything. Only by knowing the average global temperature 1,000 years ago can scientists know whether the Earth back then was warmer or colder than today.
What we're looking for is a period in the past or periods that were as warm or warmer than today. Because of course if they were that warm, they were probably that warm due to natural processes. And that might give us some clues about what natural processes, as distinct from human ones, could be causing the warming today.
Long before thermometers were invented, human beings recorded the weather.
But now we're getting near the end of the run where the CO2 level is much more than double present day.
And scientists' pronouncements about the future of the planet vary widely as they struggle to determine whether the changes in the climate are natural or caused by human beings.
A 5-degree warming will just change the whole climate system radically. Precipitation patterns will be entirely different. The amounts of precipitation will be entirely different.
The climate changes, whether or not human beings have something to do with it. You know, there's this little anomaly called the Ice Age. The Earth's climate naturally goes from its current state to having 5,000 feet of ice over Chicago. The climate is unstable.
Tonight, Nova and Frontline set out to uncover the truth about global warming. A lot is at stake.
Any new climate treaty must not result in serious economic harm to the United States. What could be more basic than that?
From the wealth of nations to the future of the planet. Are humans warming the globe? Or are we an insignificant influence compared with the natural forces which have determined the climate for millions of years?
If you sat down and said, I'm going to design a public issue that is the absolute worst nightmare of every scientist, of every communicator in the world, you couldn't do better than the greenhouse effect. You're dealing with something that's very complicated. You're dealing with something where there's legitimate uncertainty in science. It's not that people are trying to pull the wool over anybody's eyes. There's legitimate uncertainty. You're dealing with something that has enormous consequences for people. And you're dealing with something whose effects will happen 30 years down the road, you know, when they happen. And then you give people this and say, okay, do something about it.
It is, in fact, a heat wave of global and historic proportions. Much more than just
the issue is typically framed in the media as a simple question. Is it getting warmer?
Figures in from Canada today show October '98 was the warmest October on Earth on record.
Caused power dips that delayed subway service.
Unfortunately, when people talk about global warming, it's always in terms of, oh gosh, it was hot last summer. And that doesn't work because weather and climate are two very different things. Climate is sort of long-term things. Weather is short-term, daily, hourly, monthly, whatever. And what we're talking about when we talk about the greenhouse effect is we're talking about climate.
James Trefil is a physicist and science writer who has followed the global warming issue closely.
In order to say it is actually getting warmer now, you have to know what it's been in the past. And you have to know that what you're seeing is not just a fluctuation. I mean, I remember when I was a kid in the 50s hearing stuff about the coming ice age because we were in a kind of a little cold snap then. And I remember pictures in the covers of magazines showing glaciers moving down across American cities. So if you take any short-term timeline, any short-term database for temperature and extrapolate it, you can get to crazy results. In order to make an incontrovertible case for global warming, you'd have to have a long-term temperature record, centuries, that was over a large part of the globe. And so you have to look over a long term and say, what's the average been for several hundred years, and is this a significant departure from that? And that's what's very difficult to do.
Bad weather in one place at one time does not prove the climate is changing. To prove humans are warming the globe requires detailed knowledge of the entire Earth's weather over long stretches of history. And this has turned out to be an enormously complex scientific challenge.
Very brief period during the summer when the snow melts and the sediments are carried into the lake, and that settles out into the lake, and it forms these layers, just like the layers you see in a tree ring or in an ice core. Year by year, we get a nice sedimentary record.
These year-by-year variations in thickness will be used to estimate past temperatures at Lake Tuborg. A thicker layer means there was a warm spring, which melted more snow and produced more mud.
Wow, that's great. Look at this here. Wow, look at that.
This expedition yields temperature information going back hundreds of years, but in just one location. To estimate the past average global temperature, such measurements must be made all over the Earth's surface. 3,500 miles to the south, a team from Scripps Institution of Oceanography are examining the trees in Mammoth Park, California. Franco Biondi and his colleagues have done this many times.
The way the trees grow, they will cover themselves entirely every year with a new layer of wood. And if you take a horizontal section, you're going to see the width of each one of these layers.
Because trees grow all over the world, they are one of the most powerful natural recorders. Their annual rings not only give scientists a built-in date, they also contain a record of past temperature and precipitation.
Each one of these layers is an annual layer seen in cross-section. The annual layer is formed by these two portions together, the early wood and the late wood. And the width of the layer is our first indication of a climate pattern. So the narrow band that you see here indicates a year when the winter and spring were drier than normal, and then the larger layers that you see here indicate a period when winter and spring precipitation were more abundant than normal.
Trees are very common on land, but for the 3/4 of the planet covered by ocean, scientists need other recorders. Like trees, corals can live for hundreds of years and grow at different rates depending on the temperature at the sea surface. The Earth's temperature is also preserved in the chemistry of ice layers extracted from glaciers all around the world. Each natural recorder produces estimates of temperature and rainfall for a given place and time. Combining them all, scientists have been able to extend back the temperature record for the Northern Hemisphere about 1,000 years. According to this graph, published in 1999, the 20th century's 1-degree warming stands out dramatically. But what about Greenland and its controversial medieval warm period? According to the combined data, there was no medieval warm period. Specific regions like Greenland may have been warm, but the average global temperature back then was